Welcome to our video series. We will love to hear your ideas for future videos. Now, let us dive into the topic of the end of magic. In this page, we will cover the transition from seeing artificial intelligence as a mysterious, almost supernatural force to understanding its concrete mathematical boundaries. For a brief and fleeting moment in history, tools like GPT-4 made it feel like we had successfully captured pure magic inside a box. These mechanical minds wrote our poetry past our professional exams and even diagnosed complex diseases with surprising accuracy. However, as we peel back the layers of the transformer architecture, we begin to realize that we are reaching a paradigm peak. This era of AI is truly extraordinary, but it is also mathematically bounded. It is time for us to stop calling it magic and start looking at the real engineering and science that define what these models can and cannot do in the future. We are moving toward a period where the mystery is replaced by clear physical and mathematical constraints, which is actually a necessary step for the growth of any technology. The scaling wall represents a significant and frustrating hurdle in current AI development. For many years, our strategy was incredibly simple and effective. We believed we could just feed the machine more data and build increasingly massive supercomputers to achieve intelligence. This brute force approach worked for a while, but we are now hitting a mathematical brick wall. The magic is quite literally running out of road. We are observing the law of diminishing returns in real time. For instance, GPT-4 required roughly 55 times more compute power than its predecessor, GPT-3. This dramatic increase in cost demonstrates that we now require exponential resources to achieve only linear improvements in performance. We cannot simply keep building bigger boxes and consuming more electricity. The financial and environmental costs are becoming unsustainable for the marginal gains we receive. We need a new way forward that does not rely on infinite scaling, which is simply no longer a viable path for the next generation of intelligence. Let us discuss the O(n)² cocktail party problem. Imagine you are at a massive party and you are trying to track every single conversation happening in the room at the exact same time. This is effectively what the transformer attention mechanism tries to do. Every single new word or token must compare itself to every single past word in the sequence to understand the context. As the conversation grows longer, the computational cost does not just double, it explodes. This is a massive mathematical bottleneck known as quadratic complexity. Doubling the size of the context window actually quadruples the required compute power. When we talk about million token memories, the math becomes devastatingly expensive and slow. This quadratic scaling makes it nearly impossible for current models to process truly massive documents or maintain lifelong memories efficiently. It is like trying to remember every single detail of every conversation you have ever had every time you want to say a single new word. This architecture is simply not built for the long-term and massive scale required for true understanding. The autoregressive trap describes how current transformers are essentially trapped in what psychologists call System 1 thinking. They are designed to guess the next word instantly without taking a moment to pause or reflect. Because they generate tokens linearly, they lack an internal mechanism for deliberation or correction. If a model makes a tiny mistake early in a sentence, it has no way to backtrack and fix it. Instead, it simply continues to build upon that error, confabulating a path that sounds logical and confident, but leads straight into an abyss of nonsense. This compounding of errors is irreversible in the current architecture. Without the ability to rethink its steps, the model is always just one small slip away from total hallucination. This lack of internal deliberation means that the AI is effectively running on autopilot at all times. It is like a construction worker building a bridge across a canyon who cannot look back to see if the foundations are solid. If one board is placed incorrectly, the entire structure eventually collapses into the abyss below. One of the deepest critiques of current AI is that it focuses on words and not worlds. Language is actually a terrible and low-bandwidth way to understand the complex reality of our physical universe. Humans learn physics by interacting with the world, such as dropping a glass and feeling the pull of gravity. Transformers, however, do not know what a glass or gravity actually is. They only understand the statistical probability of the words we use when we talk about those things. As Yann LeCun points out, there is a fundamental lack of grounding in these models. They learn syntax and statistical correlation, but they lack a true understanding of physics causality or logic. They are essentially predicting the word crash repeatedly without ever having felt the impact of a falling object. This gap between statistical prediction and real-world understanding is what prevents these models from being truly reliable in physical or complex logical tasks. They are masters of the dictionary, but they have never actually stepped outside to see the world that the dictionary is trying to describe. The data wall is another looming crisis for the AI industry that we must address. To make matters worse, we are simply running out of high-quality human knowledge to feed into these machines. Most of the book's articles and research papers ever written by humans have already been ingested by the current generation of models. Furthermore, as the internet fills up with AI-generated garbage, training new models on that recycled data leads to a catastrophic phenomenon known as digital sickness or model collapse. We are trapped in a finite horizon where the supply of pure human data is exhausted. Static models cannot continuously learn from new experiences without undergoing expensive and time-consuming retraining cycles. We need a way to learn that does not rely solely on scraping every corner of the web for text. If we continue to feed models their own outputs, we will create a feedback loop of mediocrity that prevents any further meaningful progress in intelligence. The era of easy data is over, and we must find a more sustainable way to teach our machines. This brings us to the pivot point in our journey. We must accept that the transformer architecture, as we know, it will probably not be the one to bring us true artificial general intelligence. We have reached the limits of its physics and its efficiency. But this is not the end of the road for AI progress. In the light of new research, engineers and scientists are already building alien architectures to take its place. We are entering the post-transformer era. The next 5 years will belong to new systems that rethink efficiency reasoning and reality itself. This is an exciting shift from brute force scaling to elegant and thoughtful design. We are moving away from models that just predict the next word toward models that can reason through problems and understand the world around them. In the following slides, we will look at 5 specific heroes or new architectural approaches that aim to solve the problems of scaling data and logic. This pivot is the most important moment in the history of AI since the original invention of the attention mechanism. Our first hero is the state-space model. These models, like the Mamba architecture, offer an efficiency solution to the quadratic bottleneck we discussed earlier. Instead of trying to memorize and compare every word ever spoken in a sequence, they act like brilliant note-takers. They compress the past into a running summary that captures the essence of the context without the massive overhead of the traditional attention mechanism. This allows for linear scaling, meaning that doubling the context only doubles the compute power required rather than quadrupling it. Because of this, we can achieve massive context windows with vastly lower compute costs. This makes it possible for AI to process entire libraries of information or maintain long-term conversations without the performance of the system degrading or becoming prohibitively expensive to run. This architectural shift allows us to move past the cocktail party problem and toward a more human-like way of processing information, where we keep a summary of the past in our minds as we move forward. Hero number 2 is test-time compute. This is the reasoning solution that addresses the autoregressive trap. What if we gave the machine more time to think before it provided an answer? By using techniques like reinforcement learning and test-time compute models, like the ones from OpenAI, can explore a branching tree of thoughts. Instead of just guessing the next word, they can test out different ideas in a hidden workspace and recognize when they have hit a dead end. They can backtrack to find a better path before they ever speak out loud to the user. This shifts the computational burden from the training phase to the inference phase. It allows the model to achieve System 2 deliberation, which is slow and conscious and logical, rather than just relying on the fast and intuitive reactions of System 1. This ability to pause and reflect is exactly what is needed to solve complex math problems or write intricate computer code, where every single character matters and mistakes cannot be easily fixed later. Our third hero is JEPA, which stands for Joint Embedding Predictive Architectures. This is the world model solution championed by researchers like Yann LeCun. To truly understand reality, we need to move away from just predicting the next word or pixel. JEPA works in an abstract latent space. Instead of trying to guess every exact detail of an image or a sentence, it learns the underlying physics of the universe by predicting cause and effect. It focuses on the big picture dynamics rather than the superficial noise of the data. This allows the AI to understand causality and the way objects interact in space and time. By moving from generative AI to predictive AI, we can build models that have a much more grounded and realistic understanding of the world they are trying to describe. This approach mimics the way a child learns about the world by watching how things move and fall rather than by just reading a book about them. It is a fundamental shift toward true intelligence that understands the rules of our reality. Hero number 4 is neuro-symbolic AI, which provides the logic solution to the problem of hallucinations. To stop machines from making things up, we can combine the wild pattern recognition capabilities of neural networks with the unbreakable and rigid rules of pure logic. Think of it like a partnership between a creative artist and a strict judge. The neural network proposes an idea based on patterns it has seen, and then cold hard math and logical verification steps in to check that idea before it is ever presented as a fact. This approach grounds neural outputs by forcing them to adhere to strict mathematical and logical verifications. It ensures that the model cannot just make up a logical sounding, but false path as it is constantly being checked against known truths. This is particularly important for high-stakes applications like law and medicine and engineering, where we cannot afford even a single mistake. By merging the two worlds of deep learning and symbolic logic, we create a system that is both creative and perfectly accurate. Our final hero is the liquid network, which is an adaptability solution developed at MIT. Traditional transformers are essentially frozen in time once their training is complete. However, liquid neural networks are continuous and shape-shifting minds. They are governed by complex differential equations that allow their very structure to adapt on the fly to new and chaotic environments. They can learn continuously at the edge of the world, adjusting to new data without needing a full and expensive retraining cycle. These models are tiny and ultra-efficient because they use dynamic continuous time equations to model the world. This makes them perfect for robotics or autonomous systems that need to respond to a changing environment in real time while maintaining high levels of performance and low energy consumption. While a traditional model might get confused by a sudden change in its input, a liquid network simply flows into a new state that matches the current reality. It is a living form of mathematics that evolves along with the data it receives. The transition between these different eras is often called the messy middle. Revolutions are rarely clean or immediate. The near future will likely not be dominated by a single winning architecture, but rather by brilliant hybrid chimeras. We are seeing a trend of hybridization where different technologies are mashed together to get the best of both worlds. For example, models like Mamba interleave transformer attention layers with state space model blocks. This allows the model to keep the raw associative power of the transformer while benefiting from the endless memory and efficiency of linear models. By mixing these different approaches, researchers can capture the theoretical advantages of multiple systems, creating robust AI that is smarter and faster, and much more capable than any single architecture could be on its own. This era of experimentation is where we will see the most creative and unexpected breakthroughs as we try to find the perfect recipe for the next generation of artificial intelligence. We are currently building the bridge between the old world and the new. There is one significant catch in this transition, which we call the silicon bottleneck. Our entire global infrastructure for supercomputing was built perfectly to run the transformer architecture. The GPUs we use today are optimized for the specific types of math that transformers require. To run these new alien minds efficiently, we will likely have to invent entirely new silicon brains to house them. This is the hardware constraint that might slow us down. Future architectures will require specialized hardware like LPUs or neuromorphic chips to realize their true efficiency potential. Until the hardware catches up with the software innovations, we may be stuck running advanced new models on old and inefficient systems. This hardware revolution is the next necessary step in the evolution of artificial intelligence to support these new ways of thinking. We are currently seeing a race to build the next generation of chips that can handle continuous learning and branching logic. The future of AI is not just about code, but about the physical atoms that allow that code to run. We have reached the beginning of adulthood for artificial intelligence. The scaling laws for transformers are saturating, but this is not a crisis for our field. Instead, it is a signal that our initial period of rapid and brute force growth is coming to a close. The transformer was just our childhood, which was a necessary phase where we learned the basics of what was possible with large-scale data. The universe is vast and chaotic and beautiful, and we are finally building the specialized minds required to truly explore its depths. The end of the transformer era is not the end of AI progress itself. It is the beginning of its maturation into something far more capable and efficient and grounded. We are moving from toys to tools and from guesses to true understanding. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.